Hello. This video will talk about the mathematics of backpropagation. Now, backpropagation is extremely important in the study of neural networks because backpropagation is the way that the network is trained. The weights and biases of the network are adjusted to match the outputs for given inputs. This treatment is somewhat more mathematical than the treatment in the PowerPoint slides from Professor Kaziaskar's series. But this goes into the details of how backpropagation is derived mathematically. So let us consider the case of a neural network with a single output node with binary cross-entropy loss function. So what we're going to do in this video is do simpler cases and build up to more complicated cases. So in this case, we have a neural network with just one output node, and we're using binary cross-entropy. Now, of course, neural networks may have more than one output node and may have different loss functions, but I'll indicate how that changes the results as we go along. So, to accomplish gradient descent, we need to compute the derivative of the loss function with respect to all the parameters, that is, the weights and the biases, in the neural network. Now, gradient descent is our usual method to optimize complicated functions, and we're trying to optimize or minimize the binary cross-entropy. And backpropagation is what makes this possible. Backpropagation enables the computation of all the derivatives. I should say the derivatives because there's more than one. Each parameter in the neural network will have a derivative, will affect the loss function. And with a neural network with millions of parameters, that's a lot of derivatives. So you need a systematic way and a compact way of doing this. All right, so in this case, if I have binary cross-entropy, the loss function is here, where y is the target, and AL is the final output of the neural network. Just to remind you of our notation, in this simple neural network, we have the input layer with inputs, then we have hidden layers with nodes. Here's the final layer. In this case, we have 4 layers, so this is A1L. Okay. L is the number of layers. And this output is what's compared with the target, which in logistic regression would be 0 or 1. So that's the background of the loss function. Now the value of AL, which is the output at the Lth layer, depends on the neural network parameters, but the value of y does not. That's a given. That's something that the user supplies. So the neural network has lots and lots of parameters, as we saw here. You can see that the parameters have 3 indices. The top index is the layer. The bottom 2 indicate the nodes that are connecting. So here I'm just going to ignore the superscript and subscripts for now, just for simplicity. So theta will denote an arbitrary parameter. So this will denote a bias or weight in one of the layers. Later on, I will give the superscript and subscripts for this theta. But just to get the form of the derivatives, I'm going to use this generic theta to indicate weights. Right. So then we have, if we want the derivative of the loss function with respect to some neural network parameter, so I'm just working this through. This is common chain rule. And I put a partial derivative because we have lots of different thetas. So I'll have lots of different derivatives with respect to different parameters. So you can follow along with this algebra. And the result is this equation down here. This equation here. Now, with a different loss function, the expression will be different, but ultimately the quantities in the parentheses will all be known, and the key is finding dAl d theta. So the derivative ultimately depends on the derivative of the final output on each parameter. And in this case, it also is proportional to the difference between the target and the final output, which is a common case in loss functions. If you use mean squared error, that will be the same thing. So let's look at the first case first of no activation functions. Okay, so no activation functions and no biases. So this is a simpler case, and this is actually the case that's done in Dr. Haziaskar's slides. Then we have our final output AL. So where did AL come from? Well, AL is theta L times AL minus 1. Recall our structure here. Here's my AL minus 1, and here's my theta. Now I'm ignoring the biases and the activation function. So I'm just taking the matrix dependence of the ELF layer on the previous layer. Okay, so no biases and no activation function in this case, in this simple case. Right, but where did AL minus 1 come from? Well, that came from AL minus 2 in the same way, by multiplying by a matrix. And I can ladder this back all the way to the beginning. So AL is simply the product of these weight matrices times the original number. So the thetas are the weight matrices, as we saw. And we want the derivatives of AL with respect to the entries of all the thetas. Right? There's L different thetas. And each theta is a matrix. So there's a lot of derivatives. Now here's a key fact that matrices obey the product rule for derivatives. So for short, I'm going to use d theta to denote the derivative with respect to, that should be a theta, sorry. So later we'll replace theta with the different weights. Sorry. So what does the product rule say? The product rule says that if I have a product of different factors and take the derivative of that product, if I have n factors, the derivative will have n terms. Each term will involve the derivative of one of the factors times the other factors. So as I said, this works for matrices as well as it does for ordinary functions. Now one thing you have to be careful about though, with matrices, the order matters. You have to keep the matrices in the same order that they are at the beginning. So that's why I put the derivative of A2 after A1. So it always has to be A1, A2, A3, and so on. But in each term, just one of the factors is differentiated. So I try to explain this in words. The derivative of a product of n factors is the sum of n terms, where each term takes the derivative of just one of the factors. So I should say that the factors have to be in the same order as in the original product. All right, now, so let's take the derivative of AL, which is this product of matrices times x. Now, x is a constant because that's your characteristics, that's your features. So that doesn't change with the neural network parameters. So I'm going to take this with respect to some generic parameter and use the product rule. All right? So that means that I have L factors. I'm going to get L terms. The first term will take the derivative of the first matrix, second takes the derivative of the second matrix, and all the way down the line, dot, 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 to the derivative of the last matrix. In fact, since x is a constant, I could put the parenthesis here. So here, all that I did was, all right, so replace now these factors here with what they are. See, in this case, with no activation function, then the output of the L-1 layer is simply the L-1 matrices applied to X. The output of the first layer is going to be theta 1x, then theta 2, then theta 3, etc. So the output of the L-1 layer is going to be equal to the product of these matrices. So I just replace this series of products with the outputs. So each term is kind of like a sandwich. In the middle, you have one derivative. On the left, you have a product of the later layer matrices. And then in the front, you have the output of the previous layer. So if you want a better picture, you can write a few more terms yourself. But each term is going to have a product of matrices in front, then a derivative, then another output, a layer output. Now, these A's we've already computed using forward propagation. You needed the forward propagation to get the output of the neural network. So we already have these. So I'm going to define the matrices in front using the letter B. So B0 is I, there's no matrix in front. For the second term, theta L is in front, so B1 is theta L. B2 is going to be theta L minus 1, and so on, all the way up to K here. So you can see that the B's you can compute iteratively. If I know BK, if I know BK minus 1, I simply multiply BK minus 1 times theta L minus K. So I can compute these one by one very easily. Right? So I can simplify this expression up here by simply replacing the matrices in front by B's. Okay? All right, so now for the punchline. Remember that theta represents an arbitrary parameter of the neural network. So let's set theta to a specific value. In particular, let's say theta equals theta ijk. Now what does this mean? This is a parameter in layer K, and it's the ijth entry of the matrix for layer K. So the only non-zero derivative with respect to this parameter, theta ijk, will be in the kth layer. Right? If I have a parameter in the L-1 layer, then none of the other layers depend on it. So that means that only one of these derivatives is going to be non-zero. So it seemed like we had a really complicated expression with a lot of terms. But every time I compute a derivative with respect to one neural network parameter, I've only got one term. Now, of course, this one term involves a matrix multiplication, but still, it's much simpler than taking a sum. So I can summarize what I've been saying is that if I take theta L, where L represents a layer, and I take the derivative of theta L with respect to some parameter in layer K, then all of those derivatives are going to be zero if K is not equal to L. Now remember, L is a matrix, so there's actually not just one derivative, but there would be a derivative of every entry in this matrix. But all those derivatives are zero. So only one of these terms is going to be non-zero, and that's going to be the term that relates to layer K. Okay? So the derivative of the final output with respect to this parameter is a B matrix times this derivative, which we'll get to in a minute, times this output from the K minus 2 layer, which we've already have. So we have to figure out what is this derivative. So theta K is a matrix that includes the connections or weights between two successive layers. Theta ijk is the entry of theta K that is in row Guy in column J. The first index here is the row, second index is the column. So I'm going to define a matrix delta Kij. Right, this is a matrix, so it depends on K, I, and J. This matrix has the same size as theta K, as However, it's only 1 in one entry, and it's 0 otherwise. Right? So here I put a possible example. Delta K12 would have a 1 in the first row, second column, and 0 everywhere else. Now the size of the matrix would depend on the theta K, the transition matrix for the kth layer. But the 1 and the 2 indicate the row and the column of the non-zero entry. So this matrix is in fact the derivative that we're seeking. Because theta K is a matrix, the ijth entry is theta ijk. So only one entry of theta K depends on theta ijk, which is the ijth entry, and the derivative is 1. So in fact, the derivative of theta K with respect to theta ijk is equal to this matrix with a single non-zero entry. So I can simply put that in for my derivative, and I get my, well, almost final expression. But we can simplify this, because this is might be a big matrix, but it only has one entry that's non-zero. So what does this matrix do to the matrix product? Well, if you want to find out, you can write the product in summation notation. Recall that when you sum matrices, when you multiply matrices, the first matrix, the column, the row of the output is the row of the first matrix. The column of the output, the column of the first matrix multiplies the row of the second matrix. And then the column of the output is given by the column of the second matrix. So here I put two multiplications together. So the derivative in this case is just a number, because AL is a number. So I have this matrix will actually be a 1 by R matrix. It's actually going to be a row vector. Then this here is a R by S matrix, and this here is a S by 1 column matrix. Now when I do this sum, since delta Kij is only non-zero when R equals I only pick up the term when R equals I. Also, delta Kij is only non-zero when S is equal to J. Right? So the only term I pick up here is when S is equal to J. So I can actually just remove this delta from the sum and replace the R with I and the S with J. You can try simple examples to convince yourself that this is true. Now, I did this when AL is a number. If AL is a vector, you can do this for each component separately. So, we can actually summarize this as a matrix equation. If you recognize this, this is actually an outer product, but you have to reverse the A and the B. So it's the outer product, and you're taking the transpose. So if you want to write this in matrix notation, you can write it this way. And in fact, this gives me all of the derivatives in matrix theta K as a single matrix. So with all that complicated background, the procedure for backpropagation is very simple. First, you compute all the A's using forward propagation. Then you compute these backward matrices using B0 equals I and BK iteratively obtained from the previous, and then put them together. Okay, you can put them together using this equation here. If you look at Dr. Haziaskar's presentation of the algorithm, this is actually what he does. But here we get a little bit of mathematical background. However, things are a little more complicated than that. And this is not shown in the slides. So we also have activation functions and biases also involved. So let's look at activation functions first and see how this changes things. All right? Now before we had the final output was equal to theta L times AL minus 1. Right? But in fact, this AL minus 1 is not just AL minus 2 times theta L minus 1. Now there's an activation function. And we'll use the same activation function for all the layers. Typically, that's what you do. Okay? So the difference between this case and the previous case is you insert an activation function at each step. So the next stage would be AL minus 2 is theta, this phi, this activation function, operated on theta L minus 2, AL minus 3. So you've got this telescoping series that includes all of these thetas. All of these phis, all these activation functions. So in fact you have L minus 1 pairs of parentheses that are nested. So you have theta of something times theta of something times theta, etc., etc. And that's a little more complicated than before. But it works out not too much more complicated. In this case, when we take a derivative, we'll have to use the chain rule, because we're taking a function of a matrix times another function. Fortunately, the chain rule also works for matrices. All right. So when you apply the chain rule, well, first let's go through this. So the derivative of my output is the derivative of this matrix times this output. Here I use product rule like before. Take the derivative of the first term times the second term, plus the first term times the derivative of the second term. But I've replaced AL minus 1 with this expression. AL minus 1 comes from AL minus 2 by applying an activation function to the output. So to evaluate this derivative here, I need to use the chain rule, because I have derivative of an activation function applied to another function. So I'll take the derivative of the activation function applied at the value of the argument times the derivative of the argument. That's the standard way to apply chain rule. So I'm going to keep, so the next stage I'm going to keep this first term the same. So this is the same as the term above here. These two terms are the same. But I'm going to expand this out. I'm going to use product rule again, right? Because here I have a product, a matrix times output. Okay? So this stage is reminiscent of this stage. Right? Here I took the derivative of theta L, AL minus 1. Here I'm taking the derivative of theta L minus 1, AL minus 2. So you can guess that this procedure is going to iterate layer by layer. So here I've used the product rule. I've written this out. Now, because I have two terms multiplying this term, I'm going to distribute, and here I'm going to break this expression up into two separate terms. The factor here times the first factor plus the factor times the second factor. Okay, so I've just distributed across the plus, okay, and I get this. All right, here's my same first factor as above here, and then I've broken apart the factors. I'm going to leave this factor alone, and then I'm going to do the same thing to this one that I did before. All right, so here what I did was I replaced AL minus 2 with the activation function acting on the output of L minus 3. And I just continue. And if you follow this through, you can see that there's a cyclical pattern. I apply chain rule, then product rule, then distribute and substitute. You can see here, chain rule, product rule, distribute and substitute. Chain rule, product rule, distribute and substitute. And each time I do this, we get another term that represents another layer. Now, if you look at this carefully, the only difference between this expression and the previous expression is that you have these theta primes sandwiched in. So it's not actually that much more difficult. The theta primes are important, but they can be accommodated fairly easily. So it's still true that when we set theta equals theta ijk, only one of the terms will be non-zero. So that's how you would get backpropagation with activation functions. You basically have the same equation, but you're inserting the theta primes then the theta primes are going to influence your B matrices. In this case, your B matrix is here. So it influences the B matrices, but on the right-hand side of the derivative, there's no change. The A here is the same. So you just have to change your calculation for the B matrices. All right, we still haven't taken care of the biases. These will have derivatives also. This just adds another term at the kth chain rule step that involves the derivative of theta 0 L minus k. So that can be added also. I'll leave that as an exercise. I hope this gives you a little more insight into how backpropagation works. It looks somewhat complicated, but it's just keeping track of derivatives and using product rule and chain rule. Thanks for watching.